are going to study a system in which there is a viscous heat source. Now, all of we know that when a solid moves over another solid, due to friction, some amount of heat is generated. Liquids are no different. When one layer of liquid slips over another at high speed, that means if the velocity gradient is large, then what is going to happen is there would be some amount of frictional heat generated even in a fluid, in a liquid. Obviously, compared to solids, you need larger velocity gradients to have a situation in which heat generation is appreciable. So that we would like to have, this situation, that viscous heat generation or frictional heat generation in a liquid would be important only when there is a large change in velocity over a short distance. So, only in that case the velocity gradient would be very large and liquid layers slipping over one another would produce sufficient amount of heat which you would be able to measure. Now, in real life this situation arises in some cases in frictional bearings, because the gap between the two surfaces of the bearing is generally very small. One of them, suppose, is being rotated at a very high speed, and in order to reduce wear and tear, what we do is we add a lubricant in between the two moving surfaces. So, the purpose of the lubricant is to reduce the viscous the friction as much as possible. Now, whenever someone designs or makes such a lubricant, there are certain aspects of the properties of the lubricant which one will have to take care of. First off, it should lubricate. It should have relatively high viscosity. You do not use liquid with very low viscosity as a lubricant. It is our common knowledge that any lubricant will have high viscosity. And apart from this property, there are certain limitations of any lubricant. If the temperature goes beyond a certain point, what may happen is the components of the lubricant, they are generally not one component, they are a combination of a large number of components. The components may break down, and that is called the viscous breakdown. At that point, the lubricant loses its property, that means it no longer will be able to lubricate the two moving surfaces. So, what temperature the lubricant, what is the temperature of the lubricant during operation, that is important for the design of the lubricant. Now, suppose you have two surfaces maintained at two different temperatures, one temperature higher than the other. So, what we would assume during operation, you are measuring the temperature while the bearing is working, while the load is given on the bearing. So, if you know the temperature of the two solid surfaces, one may think that let's find out which is the higher temperature. So, that is the temperature, that is the maximum temperature that the lubricant will be exposed to. So, if that higher temperature is less than the prescribed temperature for the lubricant, then we are safe. Okay. So, we just have to find out which solid surface has a higher temperature, measure it and find out if it is within the prescribed limits. But there are certain situations in which there can be a maximum temperature, a higher temperature in the lubricant itself. That means, the solid surface, two solid surfaces may be at temperatures 200 degree and 150 degree centigrade, but in between the temperature may shoot up to 300. So, it is extremely important while operation, try to see what is the maximum temperature in between two solid plates which are moving. What is the condition? This is going to depend on the thermophysical property as well as on the operating condition of the situation. So, find out what is the maximum temperature in this flow field. That means, starting with the two solid surfaces, and due to continuity of temperature, we know that the liquid temperature would be equal to the solid temperature at the solid liquid interface. Okay. So, in between, am I going to have a maximum in temperature? If so, under what conditions? Now, without doing any analysis, I think we are in a position to intuitively say on which conditions, which are going to be an operating parameter and which thermophysical property of the liquid is going to decide about this heat generation. Okay. So, we are generating some amount of heat in between the two plates or two cylindrical surfaces. So, which thermophysical property of the liquid you think will be of importance? Thermophysical property. I am not talking about operating condition. Viscosity. Obviously, viscosity. More the viscosity, more would be heat generation. And what kind of what operating condition would you think that it's going to decide about the temperature rise? Is it okay? Conductivity. But that's a property. That's not an operating condition. So, which operating condition? Is it velocity or something else? It's a gradient. It's a gradient in velocity. How much change in velocity you are having over what distance? So, that's going to be important. So, it's viscosity and temperature, I mean the gradient of velocity, that's going to be important. Also, the temperature rise would be a function of what kind of imposed temperature difference you have between the two cylinders or the two plates. Okay. So, all these things we will have to formulate and to get a mathematical answer of the situation in which I may have a maximum in the liquid temperature in between the two plates, not on one of the two plates. So, that is a problem which we are going to analyze today. There is certain one information which you have to accept now, that is, what is the volumetric heat generation when you have this kind of a velocity gradient. In the next class, we are going to see what is the energy equation for a non-isothermal system. The same way we have derived Navier-Stokes equation, or whatever purpose the Navier-Stokes equation serves, the energy equation serves the same purpose. That means, for complex geometries and for some situations, it would be difficult to visualize what is the heat in, what is the heat out. Is there any work done by the system or on the system? Is the system having only convective heat transfer or conductive as well? So, in order to take all these things into account and give it in a mathematical form, the energy equation is derived. Exactly like Navier-Stokes equation, what you have to do is you have to pick which component of the energy equation is of relevance for the specific case. Cancel out the terms which are not required for that specific problem, and what you have is your governing equation, the same way that you have done for Navier-Stokes. But we will come to that later on. The viscous heat generation, I will give you the formula, and based on the formula we will proceed with this analysis. And in the energy equation, you would see why that form of viscous heat generation comes into the equation. Now, the system at hand is two cylindrical bearings, one, the outer one moving with some velocity. The temperature of the inner one is T0, temperature of the outer one is Tb, and let us assume that for this specific case T0 is greater than Tb. We have a lubricant in between the two, and the gap B is small, very small compared to the radius of the system, radius of the bearing. So, if this condition is satisfied, that would reduce the problem from a system of cylindrical coordinates to that of a flow between two parallel plates. So, once this condition is satisfied, we will have the top plate, Cartesian coordinate system, top plate moving with a velocity equal to r omega, the bottom plate stationary, and we already have analyzed this problem, and we know that there is going to be a linear velocity distribution. There is no pressure gradient imposed on it, no body force. So, what we are going to get is a simple linear distribution of velocity. Now, our operating parameter, one operating parameter would be omega, the other operating parameters are going to be T0, Tb, the thermophysical property of interest is going to be mu, and the geometric parameter would be B and R. Okay. So, that is how we would distinguish between the different types of parameters, properties, operating parameter, geometrical parameter of the system, which describes the system completely. Now, when we understand that if this velocity is large, if the gap is small, if the viscosity is large, then there can be sufficient heat generation inside the liquid itself because of a large gradient in velocity. So, the necessary condition for the temperature to be there would be some amount of viscous heat generation would be this one large, and B small. So, I think all of us understand up to this point. Okay. The one that you will have to accept now is the volumetric heat generation is simply going to be minus tau x z dvz dx, which if the liquid is Newtonian, it would simply be equal to dvz dx whole square. So, this is the part which I am giving you right now, and we will see why this has to be of this form. Just the next class would clarify any questions that you may have regarding this. So, this is the volumetric heat generation term. Now, if the volumetric heat generation term is of this form, where are you going to incorporate this term in your energy consideration? You have energy in, energy going out of the system. Okay. So, this is nothing but a generation term in your energy equation. All right. So, just like nuclear energy, electrical energy, the viscous energy, it's formed at all locations, and since this is linear, the amount it's formed per unit volume would be same everywhere. So, it's just a distributed source in the system. Now, we also know that the velocity in the z direction, this we have done before, is x by b and capital V, where capital V is simply the velocity of the top plate. And this satisfies the two boundary conditions, that is at x equal to 0 on the bottom plate the velocity is 0, and when you go to the top plate the velocity is equal to the velocity of the top plate. So, no slip conditions are satisfied, and this specific form of velocity distribution we have already done. So, if we incorporate this in dvz dx, what we get for SV is simply of this form. So, this would be the source term in our equation. Now, how do we analyze the thermodynamic, the thermal part of the problem? We can assume a thin strip of thickness dx, some amount of conductive heat is moving to this. So, the amount of conductive heat would simply be equal to whatever be the area of that thin strip multiplied by Qx, if Qx is the flux. The amount that goes out would be everything same, whatever be the area, only Qx evaluated at x plus delta x, and you have the source term. An interesting question can be asked is, I have said it's conductive heat, why didn't I include convective term? Can there be convection as well?
Laminar flow,
or it's one dimensional flow. Okay. And why it is, I would also say that your statement will probably be correct that it's a laminar flow. Why is it a laminar flow? I mean, the bearings are rotated at a very high speed, but even then we are assuming that it's a laminar flow. Okay. So, even though the velocity is very large, the gap between them is small. So, it has an effect of stabilizing the system. And at the same time, if you look at mu, the value of mu is large. So, viscosity brings order to the system. So, if viscosity is large, then the chances are that you are going to be in the laminar one dimensional flow regime. So, convective terms are going to be unimportant. You can safely neglect the convective term. The whole process is conduction with heat generation, nothing beyond that. So, we can simply write the the equation in difference form. This is Qx at x, where WL, these are the area ones, width and length, and this one is volumetric heat generation. So, obviously, this has to SV has to be multiplied by the volume of the system. So, which is W L delta x is V, which is mu times V by B whole square is equal to 0. So, in minus out plus generation at steady state would be equal to 0. So, any question about up to this point? Okay. So, I have written the equation in difference form. The next step obviously, as you all know, is divide both sides by delta x, take in the limit when delta x approaches 0, and what you get is the final, the governing differential equation, and I am going to write that differential equation as and what would be the next step? Substitute Qx by Fourier's first law. So, you get Qx in terms of temperature, integrate that equation twice and what you would have is T as a function of mu, V, B and what else? Should there be an x in here? Oh, yeah, right, x, this is x and this is z, all right. And what else? What else do you think could be there in the functional form of T? K, all right, let us say I have K as well. Anything else? T in the final form of T would contain mu, that we can see V B, temperature difference between the two. So, I am going to have T0 and TB or T0 minus TB, some form of that. So, these two temperatures, though not present in the governing equation, would come through the boundary conditions. The two boundary conditions that you use are going to be at x equal to 0, T is equal to T0, and at x equals plus B, the temperature is going to be equal to TB. So, I will simply write the final form. This you can do later on. T minus T0 is minus So, you get this form of the temperature distribution. Sometimes it's you would see in many engineering problems as well as in science problems, it's better to express the variables in dimensionless form. Here you have T minus T0 in Kelvin, centigrade, whatever, but commonly you would see that all these variables are expressed in dimensionless form. Can you tell us like what would be the advantage of changing something to dimensionless form, and if you are scaling it with something, what would be the value of the new dimensionless variable, range of value? 0 to 1. Why 0 to 1? No, okay, you change, divide it by something such that it becomes dimensionless. So, obviously, you have to divide it by TB minus T0. So, you get 0 and 1 at two locations, at two extreme points. But why do we express everything in dimensionless form? What is the advantage? You have done it in physics, in some other math as well. Or why do we non-dimensionalize a system? To get rid of units is obvious. That's an obvious answer. But anything? Then you can compare. Whenever you non-dimensionalize the system, there is a possibility. There are a few advantages. There is a possibility that some grouping of dimensional variables or constants is possible, which would give you an insight into the problem. For example, we spoke about Reynolds number, okay, which differentiates between whether a flow is laminar or turbulent. Now, the Reynolds number did not come on its own. If you non-dimensionalize Navier-Stokes equation, you would see that a dimensionless group will come, which is dV rho by mu, and people have found out that this is a dimensionless number. So, dimensionless numbers do not come on their own due to certain process, non-dimensionalization process. These numbers come, but they have a great utility in the sense that with the knowledge of that dimensionless number, you can compare different systems. Okay. So, you can compare between oil and water flowing through a pipe, and if the Reynolds number is same for both the cases, then you know no matter whatever be the fluid or whatever be the pipe dimension through which that fluid is flowing, the two cases are similar. They are either in laminar flow or in turbulent flow. So, that is one advantage. You can get some idea about a new dimensionless group which is going to govern that process. The second advantage is obviously computational. Here if you see, all these are may have in complex situations different orders of magnitude. Okay. So, for computational ease, it is probably better to express your variables such that they vary between 0 to 1. So, this obvious choice for non-dimensionalization for this temperature profile would be to divide it by Tb minus T0, and when you do that, what you get is some number. Just keep this 1 by 2 outside such that your T minus T0 by Tb minus T0 would simply be equal to so this number which arises during non-dimensionalization process is important, is a very important number for the design of a lubricant to be used in situations where there is a large velocity gradient. So, it is mu v square by k Tb minus T0, and if you look carefully, this contains most of the important variables which we have identified at the beginning of our discussion. It contains mu, what is the velocity with which it is moving, what is the thermal conductivity of the fluid, what kind of temperature difference you have imposed on the system. If you look at it more carefully, this term mu v square, what does it signify, or k Tb minus T0? Generally, dimensionless groups are ratios of two different things. So, if you think of Reynolds number, what is the significance of Reynolds number? Let's look at start with a very basic thing. Reynolds number is d, the characteristic dimension v rho by mu. So, if you look at this, can you express Reynolds number as the ratio of two forces? Force trying to bring order. So, where is it? Is it in the numerator or in the denominator? Denominator n or d? Mu. So, mu is the force which brings order to the system. All right. So, what is that force called? Viscous force. And which is bringing disorder to the system or can bring disorder to the system? Inertia force. So, which is characterized by this V. So, it's just a ratio of inertial by viscous forces. So, if in the same way you look at Brinkman number, all right. So, we have seen before that mu V by B square whole square, that gives you the generation of heat. So, this is the Brinkman number is a ratio of viscous heat generation, and this one k Tb minus T0 conductive heat, so the heat that is being conducted. So, it is a ratio of what is the amount of heat generated by viscosity, by viscous heating, and what is the amount of heat that is transported, that is conducted due to an imposed temperature difference in the system. So, that is the physical significance of Brinkman number. Now, if armed with this equation, you as an engineer have to find out that is there any specific range of Brinkman number which would give me a maximum in temperature in between T0 and Tb. Right now, my system is that I have two plates, one at Tb, the other at T0, and one of them is greater than the other, and there is some sort of a temperature profile which is prescribed by the equation that we have just derived. But if I have to find out whether if at a maximum in temperature exists in between these two, this is my x, the total is b, what would you do with the temperature profile that you have? My question is, with the knowledge of the temperature profile already available with you and knowing the system that it is a case of two plates at T0 and Tb, I would like to find out, is there a possibility of a maximum in between the two plates? What would you do? How do you? Okay. So, find out what is dt dx, set it equal to 0, and from that you like to see whether or not any specific condition comes out. Okay. If you do that, this is for you to do. I mean, I am not going to do that in here. What you would, when you do that, you would see that in order to have a maximum in between these two, the value, numerical value of Brinkman number should be greater than 2. Okay. When you differentiate that expression, temperature expression, equate that to 0, you would see that Brinkman number has to be greater than 2 in order to have a maximum in temperature in between the two plates. So, this is going to be extremely important for designing the lubricant. Okay. You do not need to know where, you do not have to analyze the whole problem. You know the definition of Brinkman number. For a specific operation, calculate whether Brinkman number is less than 2 or greater than 2. If it is less than 2, you are safe. Okay. The maximum temperature is going to be either Tb or T0. But if it is greater than 2, then there is a then the maximum temperature would lie in between Tb and T0 at a location in between x equal to 0 and x equal to b. If that is the case, find out what is the temperature. See if the temperature is less than the prescribed temperature for the specific lubricant. Okay. So, we would see that how viscous heat generation can be important in a real life situation. Okay. So, that was the purpose of this exercise. Any questions so far? All right. The next problem that we are going to deal is another application of this energy concept of energy being carried from one point to another by a conduction process. Now, I am saying conduction, but I am writing the title as free convection. We will clarify this anomaly very shortly. We all know what is a convection process, don't we? Like what is how do you characterize what is the characteristic of convection process? Motion of the medium, okay? Actual motion of the medium. Now, once you say convection, then you are adding an adjective in front of it saying it is a free convection. So, what is free convection and what is not free convection? So, which one is more common, free convection or forced convection? Obviously, the free opposite to free in this case is going to be forced. The name implies the definition. What is free convection?
No external forces.
No external. I didn't get it. Okay. You are probably losing some heat right now from your bodies. Is it free convection or forced convection? And if I put a fan in this room? Forced. So, whenever an external agency drives the medium against you or past you, whenever there is an externally imposed flow field, it is going to be forced convection, and whenever you do not have any motion imposed by an external agency, it is free convection. So, you do not have any motion imposed on you by an external agency, then how can you have convection? Because convection, as you have defined, it is movement of the medium around you.
Concentration gradient of the.
Is it concentration gradient or if it is molecular movement, then it is diffusive transport of energy. If it is diffusive transport of energy, I am talking about when there is movement in the molecule, but not any net motion, that is conduction. The molecule vibrates and transmits energy from one point to the next molecule, one molecule to the next molecule. Now, when you are talking about molecular motion, what kind of motion are you referring to?
Vibration.
Vibration being fixed in space. So, how can you have convection when you do not have the fan working in this room? Right, because the medium has to move.
The vibration which is not
The energy is transferred to a lower, from a high vibration, the particles near a body has higher vibration.
Okay.
They are transferred to other particles which are lower vibration.
You mean the energy by a molecule, energy gained by a molecule near a hot surface is going to be transmitted to another which is sitting next to it by vibrational motion. Can we not think a bit in a simple way, like when you put a pan of water on a flame, what happens? It does not boil immediately, but what happens? It goes up and the cooler water comes down. Why does this happen? Change of density. So, whenever you keep an hot object in a, let us say, a cold room, what happens is simple. The buoyancy changes, and as a change of buoyancy, something rises automatically to be replaced by cooler air or cooler fluid from nearby. So, that is motion of the medium near the hot object. Okay. So, that is what is free convection. So, free convection is do not impose anything from outside except a temperature gradient in between let us say a solid and a fluid, as a result of which difference in buoyancy would create a motion in there, which is natural convection. That is what we are losing heat or gaining heat or whatever. That is the most common phenomenon you can think of that is happening in nature as far as heat transfer is concerned. So, we are going to analyze the problem of free convection. Now, it sounds very simple, that liquid rising to be replaced by cooler liquid, but it is difficult to analyze most of the cases. Can you tell me why would I term the process difficult? Something rising and to be replaced by something else. What is coupled here? Again, think no hi-fi terms needed, very simple concepts. Why do you think that analyzing a system of free convection, it is not even forced convection, free convection is difficult? Do you think it is going to be difficult? Do you see different processes being coupled together? Some process the processes you have already learned in this course. It is no longer a case of heat conduction, it is a case of fluid flow as well. Whenever something rises, it is a case of fluid flow, and the rise is due to temperature, the heat transfer. So, it is a case of coupled heat and momentum transfer problem. So, whenever two different processes are coupled, that means they are not independent to each other, the analysis becomes more complex. Later on you would see that there are processes in which heat and mass transfer are coupled, or there are even situations in which all three processes are coupled. many of the situations which we deal with are where different processes are coupled to each other, and whenever they are coupled, we always first try to look at conditions or situations in which one can be decoupled from the other. So, if you think of Navier-Stokes equation and the type of governing equation for energy that you are dealing with, we would first like to see if can we decouple the two processes. If you look at the last problem that we have analyzed, the flow between two bearings or flow between two parallel plates, there also fluid flow and heat transfer together. I mean, you are having some amount of conductive heat transfer and some amount of momentum transfer. So, these processes definitely decoupled. Can you tell me what assumption makes these two processes decoupled for the problem that we dealt with? Pardon me? B is much smaller than R only helps me in changing the coordinate system, from a rather complex coordinate system to a simple coordinate system. But if I just make one statement, then these two processes are going to be coupled. You won't be able to solve one independent of the other. So, can you provide the missing statement which would make these two processes coupled? Mu, okay, fine. Mu, what happens to mu?
If mu is very large, then there is no intermixing. Means from one surface to the from lower temperature to higher temperature, the fluid is not moving, as you see in the convection.
It's a problem of momentum transfer and heat transfer. Is there any way of coupling the two problems such that I won't be able to solve one without the help of the other? That means you have to solve both simultaneously.
So, if mu is very less, that means the velocity profile doesn't depend on mu that much.
Now, if mu is very less, then obviously I would not use that liquid as a lubricant.
So, that assumption that how is that mu decreases by dx?
Someone said something about mu varying with temperature. What's your comment?
So we should take account of variation of mu with temperature.
Okay. So, you are saying if I say that mu is a function of temperature, that makes the two processes coupled. Would you agree with that? Here what we are saying is that velocity is of this form. If I assume that my mu is a function of temperature, okay, so no longer I would be able to solve the hydrodynamic part of the problem without knowing what is the temperature at a location and what is the value of mu at that point. All right. So, my hydrodynamic solution is dependent on the thermal problem, and when I come to the thermal problem, without knowing the velocity at some point, without knowing the velocity gradient at a specific point, I wouldn't be able to solve what is the temperature profile. So, that makes even this very simple problem coupled to each other, and just one assumption that mu is independent would make these two processes decoupled. So, that's a simplification. Now, we are going to look at what would happen in the case of free convection between two parallel plates and the intervening space is filled with some fluid. So, let us say I have two very long plates. This is my y direction, this is the z direction, the half gap between the two plates is B, and I have a temperature difference imposed on the system T2 to T1, and as can be seen T2 is greater than T1. So, if T2 and the space between the two is filled with some fluid, let us say it is air. So, it is a case of two vertical walls at a distance 2b apart. One wall situated at y equal to minus b is at a temperature plus T2, the wall at y equal to plus b is at a temperature plus T1. Now, because of the temperature gradient, what would happen is the fluid near the hot wall, what happens to the fluid near the hot wall? Would it rise, stay at the same place? Okay. So, obviously, there would be a motion of the fluid, general motion of the fluid in this half or somewhere close to the hot wall towards in this direction, and you can obviously see that there would be a flow in this direction in this half, or rather near the cooler plate. So you have some sort of a motion where liquid moving up to and the liquid coming down, or the fluid coming down. So you have different flow pattern in the two. What kind of a velocity profile would you think you are going to have? If let us say we let me ask the general question, what kind of a velocity profile would you have? What are the boundary conditions? Boundary conditions as far as velocity is concerned. No slip. So, at x equal to plus b and at x equal to minus b, at x equal to plus b and x equal to minus b, the velocity is going to be 0. So, this is going to be my 0 velocity plane. This is my plus z direction. So, what would happen here? Would it be straight line like this, upwards? Okay. So, it is going to be something like this, and I would not want to use the word sine curve right now itself, and over here it is going to be something like this, and these two should be connected. All right. Would it start falling again, or would it start rising here and meet somewhere in between? Okay. Now, why would it fall here? So, you are getting a maximum in velocity in this half and a minimum in velocity in this half. So, as I move away from this, the effect of buoyancy change would become smaller and smaller. So, it would come down to the case where velocity is equal to 0. So, that means, if I place a hot wall, just one hot wall in a stream of in a fluid, then there would be motion only near the plate. If I move away, far away from the plate, there is obviously not going to be any movement, the velocity would still be 0. So, that is why it would come down to it would come down to 0, it would rise back to 0 again, and as there will be a certain condition for which this is going to pass through the middle, or it can have any shape. So, we understand that there is going to be a velocity distribution like that in here. Now, we have to decouple the problem as much as possible. So it's a case of fluid flow and heat transfer taking place at the same time. Now, let us think of the case that where these plates are very long in the z direction compared to what is happening compared to the separation of the two plates, which is equal to 2b. Whenever I make such a statement, the aim is we are making the problem simpler. So, let us say we do have a situation in which z direction the plate is very long, two very long vertical plates being placed with a distance 2b apart. So, what can you say about the temperatures in between? That governing equation for this case is simply going to be d2t dy square is equal to 0. All right. I am going to have temperature. I can think of different layers, each layer having a temperature between T1 and T2, and obviously it is not a case of viscous heat generation anymore. It is very slow flow. If it is very slow flow, the temperature would be something like this, k d2t dy square. This is going to be my governing equation, and I can integrate this equation with the help of the two boundary conditions that I already have, which is that t equal to T2 at y equal to minus b and equal to T1 at y equal to plus b. One would be able to solve the temperature profile as T equal to Tm minus half delta T y by b. This you can see is going to be linear temperature distribution, where Tm is nothing but average temperature T2 plus T1 by 2. Okay. So, this is going to be the temperature profile in between the two plates. Now comes the heat transfer, the momentum transfer part. First of all, let us analyze the situation. Do we need to have a pressure gradient imposed on the system? My question is, for this case, do we have to have a pressure gradient present in the system? Do we have a body force present in the system? Obviously, yes. It's two vertical plates, so gravity is acting on it. Do we have do we need to have an externally imposed pressure, surface force on the system? Can I keep just two plates like this, okay, and not put a pressure difference? Okay, we'll see what happens. Let's say I am going to write the Navier-Stokes equation in one dimensional. So obviously the dimension of importance, the direction of importance is Vz, and Vz is a function of y. So the term that it will remain, there is no the term that will remain is this. We are going to say this is dp dz plus rho j. That's the form of Navier-Stokes equation. You all know about it. So let's not. I am not writing how we derived it. Now the assumption that we are saying is mu is a constant. Okay. Now we know that rho during natural convection is going to be a function of, what is rho function of which causes natural convection? It's a function of z definitely, but more importantly rho is a function of temperature. All right. So if rho is a function of temperature, and I would like to find out how rho varies with temperature, mathematically what can I do? And it may not be a very strong function of temperature. So if rho is a function of temperature, and I would like to find out mathematically how would a variable change, how would a dependent variable change with an independent variable, what mathematical expression would you use? A Taylor series expansion, fine. So I can simply say that rho is going to be using a Taylor series expansion and cancelling all the terms which are of higher order of this. So this T bar is a reference temperature, which I do not know what this is at this point. So this is a reference temperature. Okay. And can you give me any name for change in density with temperature at a specific temperature? Have you come across this? Something? Can you do you recognize this? Or if I say it's like this is also the same as what is this? You have studied it in thermo somewhere. What is this is called? No, it's not CP. What do you see here? Del V, del T, change in volume with temperature. Okay, you divide that 1 by V. So compared to some volume, what is the change in volume with temperature? Pardon me? Coefficient of volume expansion, and this is generally termed as beta. Okay, it's coefficient of volume expansion. How much volume change you have per unit change in temperature. So del rho del T is nothing but a function of beta. So this would then my rho would be written as rho bar. This is the density at an yet unspecified temperature T bar minus rho bar beta T minus T bar. My aim is to solve this equation. I won't be able to solve this equation unless and until I know how rho is going to change with temperature, or in other words how rho is going to change with Z, or not Z, with Y, because I know that temperature is a function of Z, and from this expression I know how rho is a function of temperature. So, in essence what I am trying to do over here is rho as a function of z. Okay. Unless and until I know the functional form of rho with z, I won't be able to solve this equation. So, my whole point is to express rho in terms of temperature, and we already know what is temperature in terms of z, such that I can find out this equation. Okay. So, what we have then is, after substitution of that expression of rho, you see we have introduced something new. We have introduced this bar here. The bar only signifies that the temperatures, the properties, the rho etc. are evaluated at a reference temperature T equal to T bar. I have not mentioned what is going to be that reference temperature. We will have to evaluate it later. Can you tell me anything about the sum of these two terms? The sum of these two terms, dP dz and rho g. Why 0? Okay. We do not have any we do not have any net motion of the system. Only motion that we are having in the system is due to density difference. So, you just cannot have two vertical plates and a liquid in between unless you provide an opposite pressure gradient, otherwise it will simply fall. Okay. So, there has to be a reference temperature at which all properties are to be evaluated, and we have assumed without specifying the reference temperature that reference property is, that reference temperature is T bar, and all properties evaluated will have a bar to denote that it is evaluated at T bar. So, if this is, then these two must cancel each other to ensure that there is no net motion in the system. So, if that is the case, my governing equation in this case would simply be equal to this. So, in other words, now I am in a position in which, provided I assume mu is not a function of temperature, the velocity, the expression, the governing equation for velocity or motion as a function of density difference imposed by temperature. Should I repeat it one more time? Okay. After all this, I have come to a point where the governing I have got the governing equation where the velocity is expressed, velocity or velocity change is expressed as a function of properties of the system and change in properties of the system imposed by a temperature difference. Temperature at any location, now we know temperature at location will be different from T bar, which is some sort of a reference average, some sort of temperature present in the system. And since you have local difference in temperature from the reference temperature, that difference in temperature would induce a change in rho, and that overall effect would induce a motion in the system. So, that was our aim, how to find out a relation between motion imposed by a change in temperature, and we know that is the definition of natural convection or free convection. How does motion gets introduced in the system as a result of temperature difference present in the system. So, now can we solve this equation right now? It is very simple. If you look at both sides, I mean we already know what is the functional form of T with respect to y, that we have derived previously, that T is equal to T m minus half delta T y by B. So, what I need to do is, from the thermal part of the problem, substitute T in here, integrate this equation twice. In what are the boundary conditions? You need two boundary conditions on Vz. What are the two boundary conditions? Plus minus B, it would be equal to 0. So, once you do that, then you get the velocity distribution, complete velocity. You read this from the book of Bud Stuart Lightfoot. Okay. I am not showing all the steps. You would see that the velocity is going to be equal to where this A is nothing but a constant T m minus T bar by delta T, and eta is a dimensionless variable which is y by b. After which one are you talking about? It's clear. Delta T is the temperature difference that is imposed on the system, T1 minus T2 minus T1. So, by using two boundary conditions at plus minus b velocity equal to 0, this expression can be obtained. And in this expression, this is 1 A and this is eta. Still one thing is unknown in the system, that is T bar. What is the reference temperature? In order to find a reference temperature, you have to specify certain certain other conditions, and the condition that I am going to specify here is that the two temperature difference between the plates are maintained in such a way that there is no net flow. You have a situation in which the temperatures are maintained at T2 and T1, some liquid goes up, some amount of fluid comes down. I can always change this in such a way that there is no net flow in between the two. That is possible. You can change the temperature differences to obtain that condition. So, if I say that the situation is such that there is no net flow between the two, what is the extra boundary condition I am providing to you?
Y equal to 0, we've got velocity of 0.
So we at that point.
Not necessarily. I would not say that at y equal to 0, that means at this point velocity is going to be 0.
So Vz at x equal to minus b equal to Vz at x equal to plus.
Vz at,
So it's symmetric.
I do not know if it is going to be symmetric, because your physical properties are going to be a function of temperature. So, how would it change on both sides, whether it is going to be linear or not, that I do not know, but I should be able to say something else, some integral of Vz over dy from 0 to whatever plus b to minus b would be equal to 0. Okay. Use this condition that average velocity is 0, use this condition and you would see that T m, that T bar is going to be equal to T m. So, this T m is nothing but half of T1 by plus T2, and another in your text you would see another form of Vz. The purpose of this exercise is to show you how natural convection works. In the simplest possible sense as well, the analysis of natural convection is extremely difficult because of the coupling of two different processes. Only by using several simplifying assumptions we were in a position to find out an expression for velocity as a function of operating parameters and thermophysical properties. And finally, the application of this analysis is in the separation of isotopes. Okay. You have different isotopes, you have isotopes of the same thing, so they are extremely difficult to separate. Thermal diffusion is one such method of separating one isotope from another. So, that is the analysis where it is used. Thank you.